Okay, let's do this question. What you have here, the blue color indicates the water. So here you have pipe. This one should be 10 centimeter. Okay, this is 10 centimeter. Okay, so you have pipe attached with a nozzle. The smallest part of the nozzle is 5 centimeter in diameter, and the water flows from point 1 to point 2 before it exits to the atmosphere. Okay, so after the water exits to the atmosphere, it hits a vertical stationary wall, meaning that this wall is not moving, so the water hit this wall. And then the question says that, this is not water, it's liquid 0.79. Okay, it hit the water, the liquid hit the wall, and the wall exert 450 Newton of reaction force from the water jet. The reaction force acting in that direction. So, and the size of the reaction force is 450. Okay, we label that to be Fx. Okay, so now the next step is since this is the information given, so we take out the control volume of the water at this area. Okay, we take out the control volume of the water here. So if we enlarge that part, actually your control volume of the liquid become something like this. Okay, where you have Fx equal to 450 Newton, and then here you have V2. Okay, and the water splits evenly upward and downward, but in this question our vertical force is not a concern because we were given the horizontal force. So with that, we build the momentum equation for this system. Our momentum equation will look like something like this. Fx, we decide our direction to be positive, negative in that direction. Okay, so Fx going to your right hand side, so positive Fx equal to, okay, this is the first the inlet. Okay, density, it is going into your control volume, so negative A1 V1. Okay, and then the velocity direction is this should be A2 V2. Okay, and the direction of your fluid is to your left, so negative V2. Okay, so with that, your Fx is equal to rho A1 A2 V2 square. Substitute the value given there, 450 Newton equal to rho A2 V2. Find our V2. Okay, plug in the values. Please remember that this is not water, it's liquid of 0.79, the Sg, so 0.79 Sg. Solve for your density, then your V2 becomes 17.03 meter per second. How do we change the density in case you are not familiar with that? Sg is equal to density of your liquid over density of water, which is constant at 1000. So density of your liquid here is equal to Sg times 1000. Okay, that will give us our velocity to be 17.03 meter per second. Okay, the first part of the question asks you to find the mass flow rate of the liquid. So we use the V2 to find m dot. M dot equal to rho 2 A2 V2. Okay, 0.79 times 1000 times with the A2 times with the 17.03. That will give us m dot to be 26.42 kilogram per second. Okay, that is our first answer. Okay, next we have to find the pressure at point 1 here. Okay, so the next thing that you have to do is build Bernoulli equation between 1 and 2. So you have P1 over gamma plus V1 square 2J plus Z1 equal to P2 over V2 square 2J plus Z2. Okay, plus HL. Over here, do we have to consider the head losses? The answer is no. How do we know that? Look at the sentence, look at the information given here. It says that if all frictional losses along the pipe are negligible. As you have learned with the Iskandar before this, HL measure is contributed by frictional loss, frictional effect. Okay, between the liquid with solid, meaning the wall or the pipe. Okay, but if the frictional losses is negligible, or if it's the viscous effect is negligible, then we can disregard our HL. So HL become 0. Okay. Oops. So with that, in our energy equation here, HL equal to 0. Okay, now let's simplify our Bernoulli equation. P1 is inside the pipe, so it has to be there. P2 go to the atmosphere, go outside the pipe. So it is equal to 0 kilopascal gauge. Okay. And point 1 and point 2 is on the same horizontal level. So with that, Z1, Z2 can be cancelled out. Okay, with that, our Bernoulli equation becomes, you can reduce it to P1 over gamma equal to V2 square 2G minus V1 square 2G. Okay, and you have your V2 here, 17.03. How do we find our V1? The answer is from continuity equation or conservation of mass. Conservation of mass equation, which is m dot in equal to m dot out. So rho 1 A1 V1 equal to rho 2 A2 V2. This is an incompressible liquid, so the density does not change with time, leaving you with A1 V1 equal to A2 V2. So with that, since you were given you have your V2, and then you were given also the dimension for 1 and 2, so your V1 becomes 4.26 meter per second. Okay, from there we go back to our Bernoulli equation here to solve for our P1. So our P1 you substitute the values, your P1 would be equal to 107.4 kilopascal. Okay, please remember here, because you have in this Bernoulli equation, in the first place, you have defined your P2 to be 0 kilopascal gauge. Automatically, the answer that you get here, your P1 here, is also in gauge pressure. Okay. Meanwhile, the question asks you to find the absolute pressure at point 1. So what you have to do is P1 absolute is equal to 107.4 kilopascal gauge plus 101.31 kilopascal. This is a constant value. Okay. With that, you'll have 208.7 kilopascal gauge as our final answer. That's it for this question. See you in our next video. Bye.